Okay, so hi everyone. Thanks so much for coming. Many thanks to the organizers, Brian and Philippe and Robert, for making this possible. And many thanks to anyone who's working today who shouldn't have been, also making this possible. So my goal here over the next few days is to give you something of a mini course on motility cohomology. And a large part of the day will be devoted to explaining to you what I mean by that and where we're going. So let me begin by recalling the situation from topology. Due to Thier and Herzenberg. From 1961, and the theorem says that for any topological space X, maybe I should have some finite condition on topological space or something, at least in the traditional context, but I'm not going to go too much about this. I can look at its complex algebraic K theory, excuse me, its complex topological K theory. And as a spectrum, this as a filtration with graded pieces given by the usual singular cohomology of the space with various shifts. So this will be my notation for the shifting of complex to the left shift. And so we get then, just by machinery of filtered spectra, we get what we call the Thier-Herzenberg spectral sequence. Which is going to converge to the topological K groups of our space, coming from all the singular cohomology groups matched together in a certain indexing, which I've chosen some algebraic indexing to match what we'll see in the algebraic context. Furthermore, everything, that is to say the filtration, and therefore the resulting spectral sequence, rationally splits simplifying the description, giving us just a decomposition of the rational topological K groups of our space as sums of various cohomology groups. And maybe at some point we can discuss the proof of this later if I want to say something about analogous machinery in the algebraic case. And the next point to recall is a little over 10 years later. This was the topological context. And then in 1973, Quillen, he introduced for any scheme, let's say, it's algebraic K theory as a replacement of the topological K theory. Which in case of any ambiguity is always going to mean for us non-connective K theory. of perfect complexes on X. It's the usual.
Rational splitting on the tensor Q on the right.
Yeah, thank you very much. Thank you. You had a bad feeling that I and I can put my finger on what it was. But thank you. And so now when we get to the quote that I just had time to write, which is due to Baylinson McPherson and Schechtman, a few years later, they have a survey paper on motivic cohomology. I'm going to be good on video. And they write in the introduction of that paper, imagine a world in which the K-theory of the topological space had been defined, but the ordinary cohomology groups had not yet been discovered. Present-day algebraic geometry is such a world. There's some dots that are maybe hard to see here. But it's part of the quote. A cohomology theory which is appropriately related to algebraic K groups has not yet been found. We have the K theory, but at time there was no cohomology theory fitting in to a similar theorem as the singular cohomology of the topological space is related to its algebraic K theory. And the existence of such a theory was then the subject of a conjecture of Baylinson and Lichtenbaum in various papers in the 80s. Now, take a little bit informally here, for any scheme X, essentially such a cohomology theory should exist. There should exist a theory of what they christened motivic cohomology, because it should be universal in some sense. This would take the form of various motivic complexes associated to X. So these are some complexes, each possible weight J. And these should be related simultaneously to the K theory of X in some similar way as in the first theorem. And then since they're also supposed to be some sort of replacement for the singular cohomology, which I can also be related to the tau cohomology, which is typically the algebraic replacement for singular cohomology. If we're working periodically in characteristic P or over periodic rings, then a tau cohomology doesn't behave well. And the correct replacement for singular cohomology in that case is something called symptomic cohomology, of which there existed some shadows already at the time, and which we'll discuss in detail at some point during the course. But now singular cohomology can also be described very explicitly. You know, we look at sort of combinatorial information of cycles and subsyntheses of the space and so on. And so you'd like some manifestation of that also here. So these motivic cohomologies were also expected to be related to algebraic cycles on X, at least in nice cases. Maybe I could put some dots, but I've already got key points on the board. Let me straight away make a few remarks about this as make it clear how this is supposed to relate to the first theorem. So this motivic complex of X is supposed to play the role of the jth copy of the singular cohomology, which is appearing in the first term. I hope it's clear what I mean by that. There's, in the first term, there's topological failure of space with breaking up into various, Z index copies of the singular cohomology with various shifts, and the J subcopy there should, the J subcopy of the singular cohomology is what's going to be replaced in the algebraic world by this Jth motivic complex of X. And once we've got the complex, there was also another whole cohomology theory, then we define the motivic cohomology groups as the cohomology groups of these complexes. And this is the standard notation for this. And similarly, if I want to study at some point, for example, motivic cohomology with finite coefficients, I take my complex, I go to mod P, and then I take the cohomology groups of that complex. We try to put this point. Framework that we're hoping for, reasonably clear. So the search for motivic cohomology has a long history, particularly in the easiest, between quotation marks, of smooth varieties. So let me tell you what is known in that case. So this is the story of classical motivic cohomology to many people, in particular Bloch, Friedlander, Geiser, Levine, Ross, Suslin, and last but not least, Vygotsky, spanning work from the 80s to the 2000s. And it says essentially that the good theory of motivic cohomology, as envisioned by Benson and Alexander, exists in the smooth test. Let me say, good theory of motivic cohomology exists. Schemes X, which are smooth either over some field or over something like the integers, building of integers of a number field. Let's say over any mixed heuristic Dedekind domain. In fact, everything works if you're smooth over a regular base of dimension at most one. But these are really the two cases that you care about. You've either got some X which is smooth over a field, or it's smooth over a mixed characteristic Dedekind domain, and I'll call that base K. It could be a Dedekind domain, but to be honest, it's probably difficult to imagine that it's for most of the statement. So what do I mean by that? So there exist these desired motivic homologies. Such that the following properties will hold. So firstly, I'm going to number these and see if the number is consistent. There's the analog of the Atiyah-Hertzberg theorems. There's a natural filtration on the algebraic K-theory spectrum of our smooth variety set. With graded pieces are the shifts in the same way as we had in the topological case of these various motivic homology complexes. And so again, for formal arguments of filtered spectra, we get an Atiyah-Hertzberg spectral sequence puts together all the motivic homologies with certain indexing and converges now to the algebraic tables of our y-test. And again, everything splits rationally, and so we obtain, for example, rational algebraic K groups of X decomposed into a direct sum of various rational motivic homology groups. We got the indexing right, J, understand. And so rationally, motivic homology is not more than data. It's the same information. Okay, but for Bayes and Nicolon, we're predicting more properties for motivic homology than just the relation to algebraic K theory. Let me just get a few some technical properties out of the way. So one of these is that motivic homology vanishes when the weight is negative. I'll come back to this in a remark afterwards. I wanted to mention multiplicative structure because this is included in one of the papers of Benenson. We have some highly coherent multiplication maps between the weight J motivic cohomology and the weight J prime motivic cohomology and outputting classes where in the weight J plus J prime motivic cohomology, more precisely, everything assembles to the infinity algebra and weighted spectra. So given that things are vanishing in negative weight, the first piece of interest is going to happen in weight zero motivic cohomology. Now, our goal is to write down somehow the simplest and most fundamental, basic, elementary cohomology that you can think of on a scheme. That could maybe, like, if someone forced you to try to come up with an analog of the singular cohomology, when you were taking your first course in algebraic geometry, what could you try to write down? Or you just take cohomology of the constant sheet. Um, 0 plus 1 is 1. Let's do actually put x. What's weight 1? What is the cohomology going to be? Well, what's this? If you start trying to analyze K theory, okay? We're trying to break up K theory into pieces that we understand. Okay, so the first piece of K theory that you understand is indeed some copy of C given by a rank map. And you've got ranks of vector bundles. So there's your Z coming from the rank. And what's the next little bit of K theory that you understand? K1 is related to units. And so that's again the next piece that we're going to pluck off using motivic cohomology. Weight 1 motivic cohomology will be given by cohomology of units, but this is going to be related to K1, so I've got a shifted degree. It's no longer occurring in K0, it's occurring in K1. And so things get shifted a bit to the right chronologically. Okay, now we can really get to some deeper properties. Motivic cohomology is supposed to be related to a tau cohomology. And in this context of smooth schemes of a field or a Dedekind domain, it takes the following form. So as long as, let me take that.
Sorry, another question.
Yes.
Is that homological or homological?
Okay. This is a fair question. I should have, how can I write this? A minus 1.
Right.
That's my convention for shifting. I think it's the correct convention. It's shifting it. A minus 1 is shifting into higher cohomological degrees. So suppose I've got some prime L, and I work on schemes where L is invertible. So if K is a field, maybe you essentially want to imagine a case where L is invertible in K, and then I'm just saying on all K schemes. If L were equal to the characteristic of K, I would not be saying anything. But I could also be in a slightly more interesting mixed characteristic case. We could be looking at Z schemes, and then I would want to only be looking at Z schemes where L is invertible. And that would be smooth. And on such schemes, mod L motivic cohomology has an explicit description. It's given by the Zariski sheafification of the following construction. So I take a tau cohomology with coefficients in the J twist, mod L, and I chop some of it off. And what I do is I chop off everything which is above cohomological degree J. Just remember what's happening up to cohomological degree J, which is the same as the J twist, and then I Zariski sheafify that construction. And maybe we can discuss in the discussion session why this truncation is something natural to occur if you've never seen it before. So in particular, this implies that the motivic cohomology of X in weight J mod L is just exactly on the nose isomorphic to the tau cohomology with the analogous twist, but only in the range where the cohomological degree is less than or equal to the weight. Because if I take cohomology, I just get that by taking cohomology on both sides of this expression. The left side is going to give me the mod L motivic cohomology, and the right side since this thing is already a Zariski sheaf in degrees less than or equal to J, Zariski sheaf of time doesn't do anything to it, and I just pick up the cohomology groups on the right-hand side, but only in that range. And beyond that, some more mysterious information appears. What one was? So then there's a similar comparison theorem, which happens is particularly implicit, let's say. Given the Ital comparison theorem, the next one is interesting when you're working with periodically in characteristic P, or periodically over ZP, or some similar case where you can't apply the Ital comparison away from the characteristic. And instead of any prime P, then we have an on-the-nose description of how the molecular cohomology looks modern. And it's a similar idea. We wish to sheepify something. And this time we take symptomic cohomology. Again, with mod P coefficients and some appropriate notion of twist. And this again is something that we need to discuss later. And we play the same game as we did in the case of the Kalpon model. We chuck away the information into the appearance into the above the weight. And we force the rest of the sheet. And that's then again a precise description of the molecular cohomology mod P. So for example, so the symptomic cohomology is something which is easy to write down in one case. So if X is a smooth variety over a field of characteristic P, then the molecular cohomology X mod P is given by the following construction. I'm going to take the tau cohomology of certain explicit sheaf that I'll define for you, and then again there's some shift into high cohomological degree. And this omega J log is giving the symptomic cohomology in this case, but as I said, it's more explicit. So this is the subsheaf of omega J. Let me just say omega J X. I look at the differential form of X, weight J, and I look at the subsheaf of that generated by things of the form dF1 divided by F1 wedged through the Fj divided by Fj as the F1 over Fj variable invertible functions on X. So I look at length J wedge product of log forms, hence the name omega J log. So it's an explicitly defined subsheaf of the differential forms. I take its cohomology, and that gives me the mod P molecular cohomology. In this case, it's smooth varieties and characteristics. Next,
So the symptomic business, what's the assumptions on X?
for this statement, it's as in the statement for part 7, it's as in the statement for the theorem. I take any X which is smooth either over a field or over a mixed characteristic Dedekind domain, And then that statement holds us. But on the category of all such schemes, that's what.
Is there some like intuition for why these log forms show up, or is that a hard one? Is it just how it works out? I mean,
If I still documentation.
Right.
There's also documentation. Maybe I can put the state. I can like your question. So in case I have a field, I have again precise description of the motivic cohomology groups in one case. When I look at the weight J motivic cohomology and I take the Hj, which is some diagonal line in the motivic cohomology, well, then I can compare it to what we call the Milnor K theory of the field K. Which is defined, I take J copies of the units of K, I tensor them all together, and I mod out by the relation that some F1 tensor through Fj, where these are all non-zeros in my field, I kill this if ever Fi plus Fj is equal to 1. No, okay, can't be J. The Fa plus Fb for some indices A and B. So it's an ad hoc form of K theory of a field, which is partly justified by the fact that it turns out to be isomorphic to some piece of the motivic cohomology. Where this comparison map is coming, we put some pieces together. From 5 and whatever the multiplicative structure was, 3. Right? But 3 was telling me that the units of my field K show up somewhere in the motivic cohomology. But 3 is saying that I can multiply things together. So if I give you J units in my field K, I can multiply them all together and produce an element in this motivic cohomology group. And then it's the theorem is that this factors through this relation and identifies the motivic cohomology group with the normal gradient. Okay, so now I can get to the previous question. Maybe so if K is a field of characteristic P, then there's a theorem of Bloch Gato and Gabor. So I can now map the normal K theory of my field to these log forms on K. And how do I do this? Well, if I've got some F1 to Fj, sorry, I didn't give myself enough space, then I send it precisely to dF1 over F1, wedge through dFj over Fj. Now, this can't be an isomorphism because the thing on the right is an FP vector space. It's sitting inside some FP linear thing. The thing on the right, thing on the left might not be, but at least if I mod it out by P, sorry, space is really hard to messed up, then that would be an isomorphism. And so in the normal K theory, which shows up as a piece of the K theory, we see these log forms. And let's say this is spreading that result out.
This is the probably.
Sorry, second.
What about if, what about question 2.8? What if K is something more complicated, like a regulated joule, so
Then I think that would be an unknown. I mean, it's only between the local case. The one case is only really a reasonable thing to consider when you have lots of units in your grid. Conjecturally, that's true in the local case for some data. Let's say you take some localization of your ring of integers, or even some localization of a smooth schema of your ring of integers. That will be true, but I believe that's unknown.
I have a question about does the definition of statistical homologies depend on which base you work?
No, that's actually a very good question. That's a very good question. And I thought for a long time about how to state the theorem. Like, so the theorem is often stated as you fix your base K, and then you have some theory of modular cohomology. So the answer to your question is no. I mean, modular cohomology should be an absolute theory, it should be like K theory. Like plug in a scheme, and out comes modular cohomology. With some of the classical constructions, that was not totally clear, and it looked as though maybe the constructions were depending on your base. Well, we know that is not the case. Like if you take care, you can see that it's not the case. It really is an absolute theory. You plug in your scheme, independent of any structure map to any base, and then modular cohomology comes out.
Okay, so the statement is like property that it admits some base.
Yeah, that's what and then in fact everything should be functorial for the class of schemes with that property. Without requiring the morphism to be compatible with that structure map. But I think it's only relatively recently that we can actually make such a precise statement. Previously, it was always assuming some compatibility with the structure. No, that's a good question. That's a good question. Okay, this is a long statement theorem, isn't it? Yeah. Again, hit double digits. Okay. Okay, so I wanted to say some. So far, we've talked about quite cohomological properties, and I wanted to finish with some geometric properties. So the projective bundle formula holds. That is to say, if I have some smooth K-scheme, and I want to compute the motivic cohomology of the projective line over X, then it's given in the usual way for well-behaved cohomology. Namely, we have a copy of the motivic cohomology of the base. And then we have another copy of the motivic cohomology of the base, but with a different amount of twist and shifted a bit. How is this given? Let me write it slightly sloppily as though I was looking at the groups. I take my class in the base and the twist and shifted copy on the base. And so the class in the base, let me write pi for the structure map of P1. I just put it back. And what do I do for the shifted twisted copy? Well, I start by pulling it back. And then I multiply it by the line bundle over 1 that I have on P1. What I mean by this, O of 1, it's a line bundle, it's sitting in the Picard group, so it's sitting in H, with the indexing, it's sitting in H1 of the thing on the right. No, it's sitting in H2. right, so on H2 of the thing on the right, because it's in the H1 of GM. So it corresponds to something in H2 weight 1 motivic cohomology. And then I'm allowed to multiply classes. So in this way, I have two obvious ways to produce classes in the cohomology of P1. I can either just pull things back from the base, or I can pull them back from a different shift and twist and multiply them up by over 1. I think that's the two obvious ways to produce classes. And if I do all that and I sum them up, I get all of the motivic cohomology of P1. And for Gaussian deflects, this was a fundamental property that if your cohomology theory did not have this property, you rejected it. An analog of one of the axioms, one of the Eilenberg schema axioms for cohomology theory and topology, that your cohomology theory behaves correctly under suspension. The replacement for that in the algebraic context, and without it, you would not even discuss it. Almost there. The motivic cohomology in this case.
Sorry, the statement, if it's an equivalence?
Yeah, so essentially, yeah, so that'd be great. So instead of trying to compute motivic cohomology of P1, we can try to compute motivic cohomology of the affine line, and then we have this homotopy invariant statement. That it didn't do anything. I just get the motivic cohomology of the base as an analog homotopy invariant in the algebraic context. And finally, I told you that the prediction that this should be related to algebraic cycles.
But is this then true for any scheme?
That's true for any scheme in the generality in which I'm stating the field.
Ah, sorry, how is this?
So this one.
Thank you.
Yeah? Okay. And so I finally wanted to finish with another case in which we can relate the motivic cohomology to a more classical invariant. Then the Chow group of codimension J algebraic cycles on your variety that shows up as the degree 2J weight J motivic cohomology. But if you see the Hertzberg spectral sequence, it will contribute to the K0 of your scheme by some standard relation between vector bundles and algebraic cycles.
So how is this map defined?
This one, how is it defined? You know, the only solution that comes to me is that I write down some Gersten style resolution with object on the left is made out, so it will be some complex computing it. And the complex which will be computing this will okay. No, here's a more tautological answer, is that the first model that we had for these motivic complexes was one proposed by Bloch, defined in fact purely in terms of algebraic cycles. There the entire complex is defined in terms of algebraic cycles, not only on S, but on various affine spaces over X, satisfying various intersection conditions. And if you look at the very, very end of the complex, this will be the top degree in the motivic cohomology, and at the very, very end, what you'll see will be precisely the usual channel.
Would this require some comparison theorem?
That does, yeah. I mean, if you just like output motivic cohomology from some machinery, say, motivic homotopy theory, that doesn't look obvious.
Maybe like cycle class.
There are many more people that
So what you add those two, those 2 plus 2 would give you 11.
That would give me cycle classes. Right, I could construct cycle classes. Right, if I had some localization sequence, I had some purity there, I could construct cycle classes. Yes, Let's go through. Yes, with some work, you could output the cycle classes in fact from K. Would be this way. We have some purity theorem to kill some motivic homologies, and then you look at your T-Hertzberg spectral sequence, and your cycle would give you a class in K0, and then some map from the T-Hertzberg spectral sequence would produce from that a cycle class in the motivic homology. That would then let you set up a candidate map level. We'll do that, yeah.
Well, I suppose you know the K equals 1, can you use the general matching this?
I don't think so, because the child group is not in general. Child groups of high codimension cycles, they don't need to be generated by the pre-buffer.
But they do need to be kind of intersections.
Yes, and so it will be compatible with intersection, but I don't think that's super defined upon that. You're going to have to write it a very small Picard group with a very big time.
So how unique is a motivic homology in the sense that does this property somehow characterize it?
I don't have an answer to that question. I don't know. I don't know. Actually, good question for this time. I don't know.
What was the question, sorry?
Somehow, if all these properties uniquely characterize motivic homology.
Yeah.
That's very good.
Is there a theory of coefficient objects or multiple homology?
Yes, but it will take us. Again, this happens something. But we're not going to need it and things to problem.
And is this always a perfect form?
No.
Already.
No, I mean it could. Ah, okay. I mean it's just a complex of Z modules. If I ask me the first complex, it's just asking those bounded in both directions. And it's always bounded chronologically above. And the question of whether it's bounded chronologically below would fall from the Bennett insulating vector, but it is wide open. I can't see another way to put that bound below. But it's just a question of whether it's bounded in the two. Okay. I wanted to make two quick remarks. There's one more here on the state. I'll get a quick remark in. Let me just make a remark orally. So there's two maybe key differences in relation to what we saw in the topological T-Hertzberg complex. So there we said the topological case theory broke into copies of the singular cohomology. And they were just all singular cohomologies. It was singular cohomology with shifted in both directions infinitely many times. And now we see a different phenomenon that we don't just pick up the same cohomology theory infinitely many times, but it changes as we move it along. And I would argue that's because topological case theory enjoys box periodicity, which is periodicity related to double suspension, related to S2, and this S2 periodicity then manifests itself that the cohomology becomes S2 periodic, and so when I shift, just get these index 2 shifts of the singular cohomologies everywhere. Whereas our replacement in the algebraic context is that K-theory satisfies the projective bundle formula, which is a type of periodicity with respect to the projective line P1, which is lurking behind as a sort of periodicity, but doesn't manifest itself in such a naive way that the output in cohomology theories are then all the same. We simply don't get that phenomenon. The other phenomenon is within the topological case, we had singular cohomologies shifted in both positive and negative. Whereas now we have the phenomenon that when we start going negative, the motivic cohomologies vanish. And I would argue that's because K-theory doesn't satisfy the tau descent. The best we can have with K-theory is that it satisfies in this negative descent. If we forced it to have a tau descent and to still satisfy the projective bundle formula, which Bertrand tells us we should always keep, then these negative twists would actually occur. We get some K-theory, and the appropriate motivic cohomology theory would then always spread out into negative two ways. But we can't see this distinction for topological theory, so automatically in the past. second point I wanted to make was that, okay, it's clear when you've got a theorem that involves 11 statements, it's going to be hard. But if you put together the relation to a tau cohomology and the relation to Milnor K theory, you deduce that the Milnor K theory mod L looks like some mod L motivic cohomology. Sorry, I'm making your life difficult. Which is then computed by some tau cohomology. So you've got an isomorphism between some Milnor K theory mod L and some tau cohomology, and that's the Bloch-Carter conjecture. That gets you a field model. So it's somehow it's a deep theorem. And I'm going to have very little to say about the theorem in this context of smooth varieties or smooth schemes for the living arrangements of the number field. This, as I said, was about the classical state of the art spanning 20, 30 years. The focus is rather going to be going beyond this theorem, eliminating the hypotheses on X. Namely, to sketch some of the ingredients that go into proving that a good theory of motivic cohomology exists, in fact, for any schema. But if we say in this view of generality, we can again define some motivic complexes such that the Atiyah-Hertzberg statement holds out before. There's a bit of filtration on the K theory of X, and graded pieces given by these motivic complexes, and I'll get a resulting spectral sequence. Everything will split rationally. The motivic complexes will vanish in negatively. There'll be a highly coherent multiplicative structure. Okay, now we get the first difference. Weight zero motivic cohomology will no longer be as simple as just the Zariski cohomology of Z. You can see this already in K theory. So we know from the first part that everything's splitting rationally. So the rational weight zero theory shows up as some piece of the rational K theory. And these rational K groups of my singular scheme X, they might appear in negative degrees. And you need to witness this already in the weight zero theory. And what happens is that you instead get the CDH cohomology. With coefficients in the structure sheet. So it's a bit more sensitive to the singular structure of that. So that's something we discussed later. Sorry?
You said the structure sheet?
I said the structure sheet, but I wrote the right thing. Yeah, thank you. The weight one motivic cohomology will agree with the cohomology of GM shifted in the same way. Given that there's now singularities appearing, it's a bit better to work with Misnevich rather than Zariski cohomology. That's not the end of the statement, or just the written of that. It agrees with that. In degrees less than or equal to 3, but not always in general. Not in general always. Okay. Again, this is forced upon you by what you see in K-theory. You see rational pieces of K-theory appearing, which have got to force this to not be the same as that rational thing. Again, we have an Natal comparison. There are not any scheme where L is invertible, any scheme where L is invertible, then the mod L motivic cohomology will now be given by the CDH chifification of the same construction that we saw in the smooth case. I take the Natal cohomology and I chop off everything in degrees above the tape twist. And so in particular, the Bayes and Lichtenbaum isomorphism again holds. That's traditionally called the Bayes and Lichtenbaum isomorphism. We've got that terminology. So again, I can take cohomology on both sides, and I'll see that the motivic cohomology with mod L coefficients might a priori involve some CDH chifification of the tau cohomology, but in fact, some classical result of Deline tells you that the tau cohomology is already a CDH chief. So in degrees up to J, this has no effect. And again, just pick up the tau cohomology on the ladder. So again, I have the desired relation to the tau cohomology in that range. There'll be some comparison to symptomic cohomology. We'll discuss it in more detail later. We have again a comparison to minimal K theory, but now it's not only restricted to fields. Okay, the previous case would be bootstrapped up to essentially smooth things of a field. But now we have a comparison to minimal K theory, which is any local ring of equal characteristic. So containing a field. Motivic cohomology, which is now defined in that degree of generality, will again identify with the minimal K theory. Or if you're familiar with such technicalities, it should be the improved minimal K theory. If you don't know about that, just ignore the physical hat, which is why I mentioned very little. And again, getting back to a question that was asked previously about this comparison in the Dedekind domain case, that equal characteristic assumption should be redundant, but with the most that is found. The projected bundle formula will hold for this, for motivic cohomology in this degree of generality. Without that, as I said, both legal fellows could reject the theory. I hope I've managed to maintain the same index there. This is not going to be A1 invariant in general. Since algebraic K theory is not A1 invariant, on general speak, if there is only a one invariant, and you have some suitable regularity hypothesis. On arbitrary schemes, it's not, so we can't expect that to look at this cohomology. And 11 is sort of, okay, let's say for X is singular variety, we can look at the same group with plane devoid of the child group of cycles in the smooth case, but I no longer impose a smoothness condition. And this seems to be a good group. Yeah, at least precise other segment. Seems to be a good group of co-dimension J cycles. Let me insert one adjective. That's here for me. Homological. If you open up Fulton's book on algebraic cycles, he defines the algebraic cycles and child groups in the generality of singular schemes, but you can't always pull back algebraic cycles through arbitrary bad maps between arbitrary singular schemes. It's the groups he defines are not cohomology fields, don't have contravariant functoriality. This is some candidate theory of child groups with full cohomological contravariant functoriality, which agrees in special cases with previous attempts at defining such groups. So the main goal of the mini course is going to be to explain to you some of the ingredients that go into constructing motivic cohomology in this degree of generality that can construct them.
Is it true that if you start with something smooth, that the two the mutable homology is up? Previous one?
I decided to stop after 11, but I could have inserted a 12. Yes. X smooth over a field or mixed characteristic Dedekind domain. ZJ mode X of theorem 1.3 agrees with the motivic cohomology, the classical motivic cohomology of theorem 1.2. And so in the case, I want to say that in the case of looking at smooth schemes with a mixed characteristic Dedekind domain, this is very recent work of Tess Luis and Ona Kudu. Yeah, this is, as I said, this is very recent. We knew this equal characteristic case previously, and they very recently established the new characteristic case. Yeah.
So in your state of 5, it's the odd one out to the name sheet quiet instead of CDA sheet quiet, but then you also say it only degrees up to 3 is, and comment a little bit more about.
Sorry, say again.
Like you say that C mode plus by 1 agrees with the negative cohomology of GM, which is down by 1. In degrees up to 3. If I CDH sheet quiet again, is it just the same? Is it a CDH sheet on both sides? Or CDH sheet on the
I tell you what, so if I put CDH here instead, then I would actually get the A1 localization of what I see on the left. They would also which would also be the CDH heapification of the left side. That's right, the two sides agree after CDH heapification. The CDH heapification of that also agrees with A1 localization of that. I can't say more than that. And I can even give you some concrete examples of very reasonable two-dimensional singularities where you look at the local ring. And so since I did a local ring, even a Henselian local ring, this would just be the unit. Because there I would genuinely see some group appearing up in the H4. Again, it's false appointed by the Hidden data. In that case, you would see your local ring would have some non-zero rational component appearing in k minus 1 or minus 2. It's as well.
And then we'll have three.
I'm really glad that I got the numbers back. Yes.
Do you also get like door maps along a tall, like fine tall maps?
In principle, not in that, but in principle. I mean, once you stick the construction into this machinery of non-A1 invariant motion spectra of another by Iwasa, it should produce transfer map in certain cases for final time figure. I'm done.